Hello. Hey, good evening, everyone. Yeah, our students are joining in, and I'm a minute more. Okay, so everyone can hear me well, right? All right, thanks. That's very nice. Thank you for your quick response. Yeah, today we are going to start our lecture 3. Basically, we are going to go through the we will go through the some of the classical data analytics and machine learning methods. So in previous 2 classes, we mainly talk about the stories happen in nowadays smart city, and also we talk about like if we want to consider a story in a reality and convert it to some AI problem or machine learning problem, we need to adopt the systems engineering thinking. We need to convert we need to apply the process modeling or process engineering ideas to model those process and systems. Okay. And based on such kind of process engineering setup, and we are able to formulate some of the existing uh, stories into some of the machine learning problems. So we need to identify what is the overall procedure in this process, what are the inputs that it is involved, and what is the output that we are going to see, and what are the data that we need to collect. Okay. So we talk about data-driven system modeling that based on using the data, how we are going to extract the or approximate the underlying model of some of the processes. And to do the data-driven modeling process, this task needs to be done via the machine learning aspect. Therefore, today we are going to start to review the classical data analytics and data mining algorithms. All right. So first, let's have a look of the very, very high level and general summary of the process of data-driven modeling. It is like a typical, it is actually very similar to a typical machine learning process. So the first of all, like based on our problem setup, we need to first collect data, okay? Then based on the collected raw data, we need to do data selection. We need to select our target data and do the pre-processing, and to do the data transformation and feature selection. And later we apply the data mining algorithms to develop patterns, to identify patterns and develop models, okay? Then by using those models, we are able to perform some, to do some interpretation and to perform some evaluation, okay? So some of the data preprocessing and pre-analytics. So once you obtain the data, and most of the time, the raw data that you collected will be usually unstructured, and it will contain a lot of noises. Okay, so those data cannot be immediately fed into any of the machine learning algorithms, or even they do not fit into your problem setup. So there are a number of things that you need to do, and more importantly is you need to do a data preprocessing to preprocess the raw data to make it into a format that your problem can consider and your algorithm can take. So basically in data preprocessing, there are a number of tasks that you need to do. It will include first that you need to know how to handle the missing value, okay, the missing data. And second, you need to do the data auditing. That means you need to correct any of the values that they are actually irregular, okay, in the they're actually irregular based on the means of or based on some of the constraints in reality, okay. Then after correcting the values, handling the missing values, and next we need to reorganize the data into a format that the machine learning algorithms can use. So after data preprocessing, there will be another very important step that before you going into any applying any of the machine learning algorithms or apply any of the data analytics tools, the first important thing is that you need to have data pre-analytics, which means you need to have actually an initial look of how the data looks like and understand how the data sets how the values are contained in this data set, and understand some of the statistics of some of the attributes in this data set, so that you will have a quick basic understanding of the values and their relationships and patterns contained in this data set. Okay, so data pre-analytics, there's no systematic format, but what people usually do is they will plot quite a number of different charts and diagrams to understand the data composition, the data distribution, and also other statistical properties of those data. Okay, so some of the usually applied techniques is that you can compute some of the statistical metrics. For example, based on each attributes in the data set. So let me draw something. So once you have a data set, okay, so we're talking about after data preprocessing, you will have an organized structured data set. Okay, so the rows describe the data points. Okay, data points. And the columns, they are actually attributes. Okay, attributes. So the first thing that you are going to do with this data set is not just throw it into a machine learning algorithms, or just split the data set and directly go into some of the data analytics tasks. Okay, so the first thing that you are going to do is that you need to understand the data. Okay, so to understand the data, you need to understand first what is the characteristics or property of each attributes. Are they all numerical values, or some of them are constants, or some of them are categorical values? Okay, so you want to check it. Basically, you can compute like the range of the values, the mean, and the variance. The range can be utilized to compute like the maximal value minus the minimal value. Okay, or just display as an interval that what is the minimal and what is maximal, and the mean and the variance, then you will know how the data values of these attributes are spread, okay, across an interval, right? And also you need to check whether there's some of the spatial temporal relationships among those data. For example, do the attributes correlated in terms of spatial mean, okay? And also are the data indexed by the time so that they are ordered and they have some temporal relationship. And you would like to use run chart to display. Run chart is like this. It's just display the variation or the trend of the value of one attributes. It's like just like this. Okay, that's a run chart. You see how the trend, how it deviates, how it fluctuates, and how it moves. And also a scatter diagram between two attributes. For example, we have attributes x1 and x2. Okay, we draw scatter diagrams. We can see how it is correlated. Okay, the dots are kind of scattered data points. Okay, and also the pie chart and the bar chart to understand the distribution or the empirical distribution of the value of some attributes. And more advanced, if you know Tableau or Tableau, you are going to apply the dashboard function in Tableau to display multiple charts together so that you can have a more straightforward look and understanding of how the data looks like. All right, so after data preprocessing and data pre-analytics, you are going to have a very well organized or very well structured and clean data set, which is much ready than the raw data for conducting any of the data mining tasks, or data mining and machine learning basically mean the same thing, okay? So in data mining tasks, there are typically two tracks. One track is called unsupervised learning, and another track is supervised learning. So to differentiate whether this task is an unsupervised learning task or a supervised learning task, basically you would like to check whether the problem has a label target, or whether the data set has a label target, or whether a label target is concerned in this data set. Okay. So this figure shows a hierarchy of how we differentiate the characteristics of different data mining methods. So first, assume we have a pool of, we can pool like all data mining methods nowadays existed in a world together as a pool. Then we can divide them, we can partition them to two sets. One is called unsupervised learning methods, another is called supervised learning methods. And the criteria of dividing them is by checking the targets in the data set, okay? Or whether they consider a targets in the data set. If the methods do not require any of the label targets, and those methods will belong to unsupervised learning methods, okay? So it means unsupervised learning algorithms. So if the methods require to have a label targets, then they belong to the supervised learning algorithms. And also based on the characteristics of the label targets, for example, if the target is categorical, then the algorithms will belong to the classification set. That means the classification algorithm. So if the target is numerical, then we will say the algorithm is a regression algorithm, okay? So they will be divided into the classification algorithms and regression algorithms. So our review will start with the unsupervised learning algorithms, then gradually move to classification and regression algorithms. All right, so let's look at the typical data-driven modeling formulation. So first, a system or a process, we have described that. Okay, it basically includes an input X, and you have some also observed outputs Y. Then your target is to identify the function or system dynamics F. Okay, so in this modeling formulation, the problem setup is very clear. We have the observed X and Y. So they are actually data points. We have those observations. Each observation is a data point. Then we need to using those data to obtain the function F, okay, which is the system, which represents or approximates the system dynamics. Then how can we do such kind of, how can we obtain the function F? How can we approximate the system dynamics? So we formulate it as a learning problem. So given a loss function L, so a loss function typically means a measure between the observation Y, the observation of Y, and the estimation of Y. And the estimation of Y describes the output of a model. So if the model can output Y as accurate as the observations, then we say the model is well developed and the model can represent the real system dynamics. So such kind of distance measure between the observed and measured Y is called kind of loss function L. And there are quite a number of loss functions, and we will describe later. We will discuss later in later classes. And given a loss function L, a data-driven system modeling task typically aims at identifying a non-parametric model G capital A, and this capital A denotes the algorithm A. So if the model G is developed by a linear regression model, then this A is equal to linear regression. And if G is developed by a neural network model, and this A is neural network, okay? And this model, the developing of this model is conducted by minimizing the loss function. And this loss function has two inputs. Its measure requires two inputs. One is the observed Y, and another is the estimated Y, which is equal to, which the estimation of Y is output by the model G developed by algorithm A and using the input X, okay? All right, then next, let's look into the different types of algorithms, learning algorithms. First, we talk about the unsupervised learning in modeling. So what is the role of unsupervised learning in system modeling problems? Where can we apply the unsupervised learning? So based on the previous slides, you will see that we always consider some outputs. That means we have some targets, okay? Then that means the problem is not unsupervised. It's a typically supervised learning problem. But that doesn't mean that unsupervised learning cannot be applied in such kind of problems. So there are some places that we can apply the unsupervised learning in system modeling problems. And there are two very famous applications or very meaningful applications. One is the dimension reduction, and another is called data compression. So what does dimension reduction mean? Dimension reduction means given a row, so I use graph to describe, okay? I saw some of the students, they're requesting to join in, but looks like I didn't prove it is fine. They will request again, okay? So assume I have a vector, which is the input, capital X. So it is a vector of attributes. So it contains x1, x2, x3, and to xn. So I can define if each of the element x is a real value, then I will define that the x vector is with the dimension is an n-dimensional input. Okay, it's an n-dimensional input. And the dimension reduction means if the n is too large, and we think that such kind of large of n is not necessary, then we would like to reduce it to another dimension, which could be chi belongs to Rm. The dimension reduction is different from the feature selection. Okay, so the feature selection means we select a subset of these elements from this set of type X. The dimension reduction means we regenerate a lower dimensional set, which they are actually different values, different elements. Okay, but such kind of dimension reduction usually means representation learning. We don't want we want the reduced dimension or data of reduced dimension. They serve as a kind of representation in kinds of information measure of the raw data space. Okay, so assume that we have chi1, chi2, then we have a chi-n. So they are different values. Okay, they don't have the raw meaning of those x1 to xn. So this is called dimension reduction. And this is usually done by using some generative models, okay, or by some unsupervised learning techniques, such as kind of autoencoders, and we will talk about that later, or kind of embedding methods. And one very linear case is called like a principal component analysis. So you want to generate 3 eigenvectors, which represent the top 80% variance of the raw data to preserve the top 80% variance of the raw data, and use these top 3 eigenvectors as a representation of the raw input space. Okay, so this is from the attribute side, we call dimension reduction. But if we look at the number of data points, for example, we have a data set. Has n data points, but this n is super large, n probably equal to 1 billion or 1 million or 100 million, such kind of large scale. And you might not need to have the machine learning algorithm or data mining algorithm to use all of the million level data points. Okay, so you just want to use a small number of them. For example, I just want to have 100 data points. Okay, 100. 100. It's 10,000. 10,000 data points. Say, we want to compress n to 10,000. Then what can we do? There must be some of the data points they have huge overlap or some duplicated observations. So one intuitive way we're going to do that is based on the attributes P, using them as the inputs. Then we can do clustering. Okay, we can clustering the data points that they share the same similarity, clustering them as one, and using the centroid as the representation of this group of data points. And so that we can reduce the size of the data of the whole data set, according to the n dimension. Okay. So we talk about the dimension reduction and data compression. We talk about that in these two stories that we're going to use in unsupervised learning. Then next, we go to the technical details of some of the unsupervised learning algorithms in data science field. So the first family of unsupervised learning methods, I would say they are clustering algorithms. They are basically utilized to do cluster analysis. We are going to talk about three selected, very popular, simple, but very powerful, very generalizable algorithms. So they serve different purpose, and we will talk about it later. So the first algorithm is called k-means. This is the big name, okay? So based on the k-means, a lot of different algorithms have been developed. And the second is called hierarchical clustering. And the last one is called density-based clustering. Okay. So before we talk about the technical details, the mechanisms and principles of these algorithms, first we'll look into what is a cluster analysis, what we want to do in cluster analysis. So basically, a cluster analysis is we want to group data points share the same similarity as one cluster. Okay, and group another group of data points share another similarity as another cluster. So the clustering algorithm is we just based on the similarity or based on some types of data properties, we make them as clusters. Okay, so finding groups of objects such that the objects in a group will be similar, they share the same similarity to one another, but they are different from the objects in other groups. So based on such kind of problem setting, there are two measures we want to consider in clustering analysis. The first measure is called intra-cluster distance, which we would like to minimize them. What is called intra-cluster distance? That means in such kind, assume that we have these three clusters, the data points are distributed like this. They naturally show some of the cluster structure. So in the first cluster, the intra-cluster distance means we randomly pick the data points within the cluster. Then we compute their distance. So we do every pair for all pairs of data points inside this cluster. We compute their distances and take an average. Then this is called intra-cluster distance. We want to minimize. And there's another type of distance is called intercluster distance. And how does intercluster distance mean? So it means we randomly pick two objects or two data points, one from each of the cluster. Then we compute their distances. So there are there are three measures for this intercluster distance. One is we compute the maximal intercluster distance. That means two data points from two clusters, they have the longest distance. And the minimal intercluster distance. That means two data points in two clusters, they have the minimal distance. They are closer, or they are closest among all other pairs. And the third measure is called average. Okay, so the intercluster distance, there are three understanding. There are three measures. One is called maximal, another is called minimal, and average. The third is average. So some of the quite famous applications of cluster analysis. So first, the cluster analysis can be utilized to understanding some of the document or texts. So we can group some of the documents related to the same story so that we will save our times in browsing. or in searching. So, and also we can group the genes and proteins that have similar functionality. So we can do a better analytics. Or we can group stocks with similar price fluctuations. Then we might identify different, the cluster of stocks which share the similar performance. Okay, and might based on their behavior and patterns identify some secrets behind it. So in the right side, the first one, it shows the different industry groups, okay, and the different articles, okay, discovered clusters. And the lower one means the we do the clustering to analyze the precipitation in Australia. So we make the whole region by using pixels, and we annotate the pixel with different colors to indicate the clusters of the regions. They share the similar precipitation record. Okay, so the major efforts of doing cluster analysis is we want to extract some of the stories by examining the similarities among data points. And also we want to reduce the large data sets by grouping the observations. They share high similarity. Okay. So so the notion, next we would like to talk about the notion of a cluster. And it could be very ambiguous. It really depends on the angle and the direction that you look into the data point. For example, if we don't look at the other figures, we just look at the figure on the top left, you see they are just kind of 20 data points distributed in a two-dimensional space. And then based on those data points, how many clusters they should form. If we use different notations to annotate different data points, we will immediately find out we could make them into 6 clusters. We can also make them into 2 clusters. And it also makes sense that we can make the data points into 4 clusters. Does any of the cluster have a better meaning? Or which one is the most correct one? There's no exact answer to this problem. It really depends on what kind of measure you would like to consider in doing clustering, or what kind of knowledge or patterns you would like to extract from the data point. So unless your data points have some ground truths, that means from some of the way, it could be domain knowledge, it could be some of the scientific principles, it could be some of the simulations that you already know, the ground truth models. Then you have the true story to tell the pattern of those clusters. Otherwise, it is very difficult to differentiate which clustering presentation or the number of clusters have a better performance or have a better meaning. So there are a number of ways or number of different types of clustering analysis. So from the previous slides, we have talked that a clustering basically is to develop a set of clusters based on evaluating the characteristics of the data in the data set. And different types of clustering, there's one important distinction between the types of clustering is based on their principles, the hierarchical clustering and partitional clustering, they are different. Okay. And also based on hierarchical clustering and the partitional clustering, the sets of clusters developed are also different. So the partitional clustering analysis is that given a data set, a full data set of endpoints, we would like to divide the data objects in this data set into some of the non-overlapping subsets. And these non-overlapping subsets, they are actually clusters. And such division we would like to do such that each data object is in exactly one subset. Okay, so in this divisional partition, there's no ambiguity. One data points or data objects, they could only belong to one cluster. Okay, there's no argument that one data point belongs to two clusters. You have to pick, okay, one cluster for the data point. All right, so that's partitional clustering. The partitional clustering means you would like to divide a full data set into some non-overlapping subsets. And second is called hierarchical clustering. It is a reverse idea, okay? So the hierarchical clustering starts from one data object in the data set and using the nested cluster ideas to gradually include more data points to grow into a larger cluster and include more to grow into another larger cluster. And you repeat that until you include all the data objects in the data set as one cluster. Then you will have its nested cluster structure. And so these nested cluster structure form a hierarchy. So you will understanding the relationship between or among different data points. So some graphical illustration of the partitional clustering. Given the original data sets, we have those data points distributed across this two-dimensional space. Then a partitional clustering is we are going to split it or separate it into a number of clusters which are not overlapped. Okay, so this shows kind of partitional clustering. And the hierarchical clustering is different. So it basically using a kind of starting with the one data points and include another data points to form the first cluster, and to include another to a bigger cluster, and here you include all the data points in one cluster. So you have a nested cluster structure, and you can use a dendrogram to show the relationship, basically the distance, okay, among different data points in this cluster. So the traditional hierarchical clustering is nested. There's also non-traditional hierarchical clustering, although it is nested, but it is not strictly nested. That means some of the inside clusters, they are actually, divided. All right. So this is also non-traditional dendrogram. So one important issue of using or applying clustering algorithm is we need to first consider our real problems, whether they are actually a clustering problem. So you need to map the clustering problem to a different problem, okay? Basically, we want to map the clustering problem to a different domain and solve a related problems in that domain. Okay. So for example, we can first using a proximity matrices, which defines a weighted graph. So where the nodes are the points being clustered, and the weighted edges represent the proximity between points. Okay, so this is one use of a clustering. And the clustering is equivalent to breaking the graph into connected components. So you have a graph topology. You can chunk the graph connections into different clusters. Okay, and you want to minimize the edge weights between clusters and maximize the edge weights within cluster. And also in clustering, the characteristics of the input data are also important. First, we need to consider the type of proximity or the density measured in the data points. Okay. So whether data points are central to clustering, whether these data points are also depend on. So the proximity or the density measured also depends on different data characteristics and applications. So data characteristics that could affect the proximity or density, they include first the dimensionality. So usually a high dimensional data space, they typically introduce the sparsity, okay, or the sparseness of the data point. And also the attribute type, whether they are all numerical or they just contain some discrete values or some kind of. And whether there is some special relationships in the data. For example, whether some of the data points they are autocorrelated, and also the distribution of the data points. And last is the noise and outliers in the data set. So they often interfere with the operation of the clustering algorithm. Okay. So first, let's look at the K-means clustering. It's a basic principle. K-means clustering is super simple, very straightforward. It is the most famous and widely considered partitional clustering approach. What we call K-means, it is the K indicates the number of clusters we would like to partition. Okay, and this capital K usually is specified before we applying the clustering algorithm. That means in using the K-means, you need to determine the value of K. And such kind of determination can be arbitrary or can follow some numerical process. And in K-means clustering, each cluster is associated with a centroid. And this is also indicates the meaning of this means. That means we have K clusters. Each cluster is represented by the mean, which is usually the central or the center point. And each point is assigned to the cluster with the closest centroid. That means the data points you want to determine which cluster the data point should be assigned to. You need to compute the distance between these data points to all these centroids, and you find the closest one, and you assign the data points into that cluster. So the basic algorithm is very simple. First, you need to specify K, and from the data set, you need to select K points from the data set as the initial centroids. Okay, you need to initialize. Then you need to repeat the following two steps. First, based on the preset initial centroids, you need to first assign the data based on the closest centroids to form K clusters. You assign all the data into K clusters based on the distance between the data points to the centroid. Then next, you recompute the centroids of each cluster after the assignment of the data points is complete. All right. You repeat these two steps until the centroids don't change. That means the algorithm converges and you stop there. Okay. You won't make any modifications. Okay. All right. So we probably stop here. take a 15-minute break, and we come back at 8, then we will continue. Okay. Oh, sorry. Yeah. No. Your Zoom is okay. It is because I forgot to release. I will release the second lecture. Okay. I forgot to release my Zoom record of the second lecture. Let me do it. Sorry, I was too busy. Hello. So we come back and continue our lecture. Okay. All right. So we have talked about the K-means principle or mechanism in the previous lecture, and next let's use visualize how the K-means clustering works over different iterations. We see that it is there's a repetition. That means it's a iterative process. You need to repeat iteration by iteration, so it is iterative. Then next we see how does it work iteration by iteration. Okay. So first assume we have a data set. In the iteration one, we have a data set, a set of data objects spread or distributed over this two-dimensional space, X, Y. Okay. So we randomly pick 3 data points as the initialization. You can see this cross sign. Okay. It is on each of the selected data objects. Then we compute the distance of different data points to each of the centroids. All right. Then we assign each of the data points to the cluster by the criteria that its distance to the corresponding centroid is a minimal one. Okay. So after assigning all the data points into each of the clusters, then next we need to do updating of the centroids. And this updating means we recompute the average, okay, the average of the data points distance in the cluster. Then you will see that naturally the centroids will move. So this green cluster, the centroids will move towards the left bottom direction, and the centroids in the dark blue cluster will move towards the right bottom. Okay. And the red cluster, it will not move too much. It will move slightly. And after the centroids, they're updated, then you need to reassign the data points into each of the cluster based on the new centroids. Then you assign them into clusters. After assigning all of them into clusters, then you do the updating, you do the recomputation, then the centroids will move again. So you repeat that to iteration 4 to iteration 5. Then you will see that the centroids will stay in a cluster. It won't move quite much, iteration by iteration. Okay. Basically from iteration 5 to iteration 6, it doesn't change a lot. That means the algorithms converge. So it will stop there. So some of the technical details in K-means clustering implementation. So first we have talked about the centroids can be randomly picked by just using some of the existing data points in the data set. That means given a data set, there are so many number of data points, and we randomly pick k of them as the initial centroid. So initial centroids need to be chosen randomly. But the way of randomly choosing the initial centroids could be quite different. Okay. And different selection of the initial centroids will subsequently affect the clustering results by implementing the K-means algorithms. So clusters produced could be quite different from one run to another. And these differences comes from the randomly choices of initial centroids. I mean, just one of the factor affect the clustering results. And the centroid is typically the mean of the data points in a cluster. What does that mean? It's typically the mean of the points in the cluster. The mean, or basically the average of the points, they are kind of statistical metric. Sometimes people can change it to another criteria. For example, you can change the mean to the median. You will select the median of the points as the centroid. Okay? So you could make such kind of changes. But typically, we use the mean, okay, because it calls k-means. Use the average. And the closeness of the data point to the centroid is usually measured by the Euclidean distance. Okay, it is usually measured by Euclidean distance. We usually use Euclidean distance. But such kind of distance can also be changed due to different application needs. You can change the Euclidean distance to some cosine similarity or to some other correlation measure, okay, to indicate the closeness. It really depends on the data set you have preliminarily understand. Okay, that means you conduct some preliminary or analytics we have talked in the previous class, in the previous lecture. We mentioned that we probably use some of the figures, some of the charts to understand the relationship among the data points. Okay, so you can basically check whether the distribution of the data points, they follow some specific shapes, and you have to use some specific measure to push your clustering algorithms to move that way. So the k-means will converge for common similarity measures mentioned above. Okay. K-means will usually converge for common similarity mentioned above. And k-means convergence mostly happens in the first few iterations. That means its convergence is pretty fast. And based on our practical experience, it usually converges after a number of iterations. It won't take a very long time. So it's pretty quick one. And often stopping condition is changed to until relative few points change clusters. What does that mean? So sometimes if you want to strictly make sure the convergence happens by checking that the centroids will not move and the data points will not be changed. Data points in each of the cluster will not be changed over a number of iterations. But that's a way too strict criteria or way too strict condition. Sometimes they won't affect much. You could actually stop the algorithm earlier. So some people will adopt a new criteria or relatively loose criteria that we are able to tolerate just some of the points change in the clusters, very few, okay? We don't follow the very strict that none of the points change within the clusters. It is acceptable to facilitate the computational process. The k-means clustering complexity is described as a big O in terms of 4 parameters, which is a big O, and its input is n multiply capital K multiply capital I and multiply D. So in this complexity notation, the little m means the number of data points. So you will know that k-means computational cost will be increased by the increase of number of data points in the data set. The larger the data point, the larger the data set is, the k-means will take longer time. Also, the setting of the number of clusters also have a positive contribution into the complexity. That means if you would like to generate a larger number of clusters, it will take a long time. And the capital I indicate the number of iterations. So sometimes it is not controllable. The number of iterations is not controllable if you adopt a stopping condition that relatively few points change in the clusters. Okay, so this is a very this condition will change case by case in terms of the number of iterations. Some of the data set you probably take, 10 iterations, so it converge. So some of the data set you can take 100 iterations, it converge. Okay, so it could be different over cases. So some of times people will specify, they will adopt two types of conditions. One is the algorithm converge, means until relatively few points change in the clusters, or a number of iterations is reached in the implementing this algorithm. So once you can specify the number of iterations, you can have a control of the complexity. And also the last one is the little d, which indicates the dimension of the attributes, the input space, the number of the attributes involved in the data set. So the number of attributes is the criteria you utilize to do the clustering. So you measure the distance between two data points. You will actually measure the distances among each of the attributes between the two data points. Okay, so the number of attributes, the larger number of attributes also will increase the complexity of implementing the k-means. Okay, so we have talked about some technical details in implementing the k-means algorithm. Next, we need to talk about how we are going to evaluate the k-means clustering performance. That means how you are going to evaluate the clusters generated by k-means. Are they good results or not good results? So the most common measure is called sum of square errors, SSE. Okay, so where does the error comes from? So for each point, the error actually is the distance to the nearest cluster. So this error is not the error in the regression problem that the observed data and estimated data, their distance. Here, the error indicate the distance of a data points to its nearest cluster. Okay. And to get the SSE, we square these errors and summate them. Okay, then we got the sum of square errors. We do the summation across different number of clusters. You can see this X belongs to each of the cluster I. Capital CI means the cluster I. We calculate the square of the distance between the mean MI of the centroid of the cluster and also the data points X. And we do the cluster with the instance from I equal to 1 to capital K. So you have capital K clusters. Okay. We compute the distance among all the data points in a cluster CI to its centroids MI. Okay. Then we further summate for all clusters, K clusters. So here is, so X is the data points in cluster capital CI. And MI is the representative points for clusters capital CI, basically the centroids. Okay, the center of the cluster, mean of the cluster. And given two set of clusters, so if you have different clustering algorithms produce different cluster results, that means produce two sets of clusters, we prefer the one with the smallest error. That means smallest SSE. So if we have the algorithm produce different sets of clusters, we prefer the one which results in the lower SSE. And very interesting thing is, if you use a k-means, and there's a very easy way to reduce the SSE by increasing the value of capital K, the number of clusters. That means you are able to have clusters with a small number of data points, but they are actually attached quite closely, okay? But that doesn't mean that you infinitely increase K is the best results. No, there's a trade-off. So a good clustering with a small K can also have a lower SSE than a poor clustering with a higher K. Okay, so there's a trade-off. You will find out optimal K, which leads to the lowest SSE. And this will also be another way. That's the another way I have talked to determine the value of capital K. So remember, previously we talked about that K needs to be specified. The capital K needs to be specified by implementing this algorithm. Okay, before implementing this algorithm. So how to specify K? You could arbitrarily determine, or you have some prior knowledge about it. Or if you have no knowledge about it, then go with this kind of iterative process. You try different value of K, and you find the optimal K that has the lowest SSE. Okay, then the K will be optimal. All right, so normally, let me draw a figure. Normally, if we have this chart, the y-axis is the value of SSE, then the x-axis is the number of K. Okay, basically you start with 3, 5, 7, 9. Sorry, I just use odd numbers. Or you can use 2, 3, 4, 5, 6, 7, 8, 9. Assume you change K from 2 to 9. Okay, I omit 1 here. So basically, you probably will have such kind of curve. Okay, so probably around 7. My bad drawing. Probably around 7, you got the lowest SSE. Then this 7 will be picked. You will set K to 7. Okay. But this requires a kind of a long trial process. You need to set K equal to 2 to do one type of clustering, one time of clustering. Say K equal to 3, you do another time of clustering. Okay, you actually epoch by epoch, then finally you find out the curve. Then next we talk about limitations of k-means, that the scenarios k-means will not be a good choice. So k-means can have problems when clusters are of different, differing first sizes, okay? And the second, densities. That means different clusters, they have different densities, okay? And also the data points, they don't their spatial relationship do not have a non-globular shapes. Okay. So if this exists, the data have different density shapes and different sizes, and non-globular shapes, the k-means will not be good. And also k-means can have problems when the data contains quite a number of outliers. Okay. If data contains a lot of outliers, k-means can also be affected a lot. Especially, for example, so you have data points like this, Okay. You have another set of data points like this. Okay. Then you have some outliers here and here and here. Okay, you have some outliers like this. Then when you do the computation, then your central probably stays here due to the impact of the outliers. Okay. So differing sizes. Sorry, the visualization of the cases that k-means have limitations. So let's look at the first case, differing sizes. Okay. So if we know the ground truths, that original data points, they have a number of clusters. Naturally, they are in clusters, but the clusters have different sizes. Then if you apply k-means with 3 clusters, it probably will return such kind of results to you. Visually, we will know that such kind of clustering results does not make any sense. Okay, so it's a very poor clustering results, which do not return the knowledge we expect. So different sizes could be a killing point. And the second limitations of the k-means, this is the third cases, is non-globular shapes. Okay, so you will see the original data points, they are actually grouped like this. It's not like bubbles. So if you do k-means, you will return such kind of clustering results, which do not match our expectation. All right. So does there exist any techniques can handle those scenarios? Yes, we will talk about it later. And also in different densities. I didn't show example here. But such kind of cases later we will talk about it can be well handled by kind of density-based clustering. Okay, the DB scan we'll talk about later. Oh, solutions of choosing K, actually I have talked about it. Okay. There are 2 ways to determine K. First one is to use trial and error. Arbitrarily set K to some values. And the second is called iterative heuristics. This one I have explained it before. That means you can set K from a value 2 to a maximum value, for example, 25. Then you apply k-means with k equal to each of those values, and you will get a curve. Okay, then there's a kind of k value which is optimal because its SSE is the lowest. Okay, so that's all about k-means. It's pretty simple. All right. Any questions and comments so far about k-means? No questions? Okay, good. So k-means is a partitional clustering strategy. And next, we would like to talk about the hierarchical clustering. It is another idea, another type of clustering idea. Okay. So the hierarchical clustering strategy, basically, its output is not a separate, it's not a number of separate, not overlapped clusters. It is producing a set of nested clusters organized as a hierarchical tree. So organized as a hierarchical tree is because the nested clusters can be presented by a dendrogram, which looks like a tree. Okay, can be visualized as a dendrogram, which is a tree-like diagram, which records the sequences of merges or splits of the clusters. Okay. For example, here we have 1, 2, 3, 4, 5, 6 data points. And by applying the hierarchical clustering, there are 5 clusters produced, and they are nested. Okay, so we'll see that first iteration we cluster data point 1 and 3, and the second iteration we cluster 2 and 5, and the third iteration we cluster 2, 5, 4. You can see 2, 5, 4. That's the third iteration, and the fourth iteration we merge 1, 3, 2, 5, 4 together, and then we merge 6. Okay. Then based on the dendrogram, how can we see a sequence? Okay, so the lowest value presents the first iteration. Okay, then the second iteration, third, and fourth, and the fifth. Okay, that's the order. So what are the advantages or strength of the hierarchical clustering? So the first strength, compared with the k-means, is very clear that hierarchical clustering do not have to assume any particular number of clusters. So you don't need to determine k. Okay, it is an automatic procedure. You don't need to specify any number of clusters you would like to produce. It is automatically done. Okay. So any desired number of clusters can be obtained by cutting the dendrogram at the proper level. So for example, if you say, okay, for these data points, I would like to have just 2 clusters, then I will do cutting here. Okay, then we have 1 cluster here and another cluster here. Okay, so if you want to split, you can determine a way to cut. Okay, then to produce the separated clusters. And they may correspond to meaningful taxonomies. Okay, for example, in biological sciences, okay, the animal kingdom, we want to build up a kind of topological knowledge graph for the animal kingdom, and phylogenetic reconstruction. Okay, so in these examples, there will be 2 types of hierarchical clustering strategy. One is called agglomerative, and this one is more widely utilized. So this agglomerative strategy of hierarchical clustering, it starts with the points as individual clusters, and at each step you merge the closest pair of clusters until only 1 cluster left. Okay, so basically its idea is you start with the data objects, scattered data objects as individual clusters, and start to merge them and until you get 1 cluster containing all the data points. And the second way of doing hierarchical clustering, which is more rarely seen, which is called divisive. Okay, divisive. This one is less applied. Okay, it's not very frequently discussed, but it is a feasible way of doing hierarchical clustering, although its principle is not that well developed compared to the agglomerative hierarchical clustering. Okay, and most of the time people talk about hierarchical clustering, they refer to the agglomerative hierarchical clustering. So the divisive is a kind of reverse way. You start with grouping all data as 1 cluster, then you start to split. Okay, you start with 1 all-inclusive cluster, and at each step you split a cluster into 2 until each cluster contains an individual point. Okay, And the traditional hierarchical algorithms use a similarity or distance matrix. You use the similarity measure or distance matrix to determine the merge or split one cluster at a time. So we will focus on talking about the agglomerative clustering algorithm or agglomerative hierarchical clustering. It is the most popular hierarchical clustering technique, and its basic algorithm is very straightforward. The first one is based on the number of data points. You first compute the proximity matrix. The proximity means the similarity or distance or closeness between each point to all the other points. Okay. And at each data point, you let each data point be a cluster. So each one will be a cluster. Then you repeat the following two steps. You merge the two closest clusters. And at the beginning, which means you merge two closest data points. And after merging, then you need to recompute the proximity matrix. Okay, the proximity matrix. Because after merging, the clusters become one data points or one data object, then you need to recompute the proximity matrix. You repeat doing these two steps until only a single cluster remains. So the key operation is the computation of the proximity of two clusters. So how can we compute the distance between two clusters? So there are different approaches to defining the distance between clusters, and depends on the different algorithms. Okay. So the starting situation in a agglomerative hierarchical clustering. So every time when we start with the agglomerative hierarchical clustering, we start with clusters of individual points and the proximity matrix. For example, we have 12 data points. They distribute in a two-dimensional space like this. And we will set each of the data points P1 to P12. This is just an index to denote each of the data points. So the proximity matrix is the distance. For example, P1 to P1 is always 1, and P1 to P2, and the distance between P1 to P3. Okay. And so kind of, you do a computation. P1 to P1 is always 0, yeah. And P1 to P2, okay. You can use Euclidean distance to do a computation. So starting situation is very simple, all right, because you are dealing with individual data points. The complexity comes from the intermediate situation. So after some merging steps, now we have some clusters rather than data points. For example, here we already group like P1, P2 as one cluster, P3, P4 as another cluster, okay, and P10, P11, P12 as another cluster. So you now have 5 clusters. Then each cluster has a number of data points. Then how can we determine the proximity among the clusters? Then the key situation here is the selection of distance measures. Okay. So if we have a proximity matrix computed, then the merge also happens on the 2 closest clusters. Okay, so we merge 2 closest clusters based on the proximity measure and do the update of the proximity matrix. But the question is, how do we update the proximity matrix? Okay, and this refers to the different choices of intercluster distance. So how can we compute distance between clusters here to update the proximity matrix. So there are 4 types of distance measure that we're going to compute, or we can select. We can have the minimal distance, the maximal distance, the group average, and just the distance between 2 centroids. Okay. So the minimal distance means the distance between, we pick out 1 data points from each of the cluster. Okay. Then we compute their distance, and we find out the minimal distance among them. Okay. Basically indicates the closest distance between 2 data points in 2 clusters. Okay. So this figure well illustrates the situation. The max distance means the farthest distance, the farthest pair of data points. So 2 data points, they have the longest distance. They're most far away from each other in 2 clusters. Okay. The group averages, we compute the link between everyone. This is a good question, but there are, as I said, there are like different choices. So I need to describe different choices. Okay. So the last one is compute the centroids of each cluster. So the group averages, we consider all combinations of the pairs of data points in 2 clusters, and we compute the distance based on each combination. Then we take an average. Okay. So you see these data points can link to this one, to this one, this one, and that one. So there are 4 distances. And the second data points also have 4 distances. And the third one and fourth one. So they have kind of a large number of links. Okay, they will compute the group average. And the last choice is we first compute the centroid of each of the cluster, then we compute the distance between the centroid. And definitely, directly do the centroid computation, it saves the most energy in computing, save the most resources in computing. Okay, no matter in the previous min or max. So here you have a search process. You still need to compute like all the links among the data points and select the maximum one. Okay, and the minimal one. And the group average is directly you compute all of them, then do an average. Okay, and the centroid is the most simple one. So the minimal distance called single link. That means you have an agglomerative hierarchical clustering considering single link. This means the proximity of 2 clusters based on the 2 closest points in the different clusters. Okay. So determined by 1 pair of points, by 1 link of in the proximity graph. Okay. So you have 6 data points. Here the distance matrix is like this. When you do the merge, you consider sorry. Yeah. So when you do the merge, you first consider the lowest distance, okay, that you go with. So what is the lowest distance? It's a distance between 3 and 6, which is 0.11. So you merge these 2 first. Okay. So after merging these 2, then you still use the minimal distance. So this 1, 2, 4, 5, you compute their distance to the closest distance. Okay. For example, you probably compute the distance 1, 2, 3, and 1 to 6. and you pick the lowest one as a record to update. Okay. Then you will find out 2 and 5. What is the 2 and 5? 2 and 5.14. Okay. That's the second lowest. So you have to go with it. Okay. So 2, if you merge 3 and 6, and the distance between the point 2 to that cluster will be 0.15. Okay, because the distance between 2 and 3, they are the closest. But based on the minimal distance, the single link, we consider the point 2 to the cluster of 3, 6 is the distance minimal between the distance between 2 to 3 and 2 to 6. Okay. Let me notate. So it could be a little bit unclear if I just describe. So after merging 3, 6 as one cluster, okay, then the proximity, the distance between 2, so we denote this as cluster 1. Okay, between 2 and cluster 1 is the minimal value from the set of the distance between point 2 and 3, as well as the distance between 2 and 6. Okay. And for 1, the same story. For data points 1 and C1, the same story. The minimum between D13 and D16. Okay. The D indicates the distance. All right. This is this single link. Okay. So you will see that based on such kind of setup, 3, 6 will first merge as cluster 1, then next 2 and 5 as another one, then 3, 6, 2 and 5 they merge together, and then include number data points 4, and lastly include the data point 1. Okay. So this is the hierarchical clustering with the minimal link, the strength link. Okay. So it can handle the non-elliptical shapes. So you have original points. They don't have elliptical shapes. Okay. There's some kind of lines. So you can group like 6 clusters based on hierarchical clustering. But the limitation of the hierarchical clustering with single link is that it is very sensitive to noise and outliers. So original data points like this. Okay. So if you consider them to build 2 clusters and 3 clusters, so the last cluster will be like this. Okay. So it will be sensitive to the noises and outliers by using a single linkage. And next, how about the max, the complete linkage? That if you're using a hierarchical clustering, consider the max distance as a computational of the proximity of 2 clusters, then it is called hierarchical clustering with complete linkage. The overall logic of the complete linkage is similar to the single linkage, but you just replace the proximity computation from taking the minimum to taking the maximum. Okay. You determine the farthest distance between 2 data points in 2 clusters. Okay. Then again, you have 6 data points, and their distance can be computed like this. Then next, what are the data points that you would like to merge? So first, who you are going to merge? you're still going to merge with the best proximity, right? So still 3 and 6, you merge together. Okay. Then what? Then you compute the farthest distance. Okay. You will compute after you merge 3 and 6, then the distance between each of the remaining data points to that cluster is to compute the farthest distance. It can be written as this. I use data point 2 as an example. If we denote the cluster of 3 and 6 as cluster 1, then 2C1 will be equal to the max of D23 and D26. The updating of the proximity matrix will be we're using such kind of equation. But the cluster, merging the cluster, the formal cluster, still consider the minimal of the minimal proximity. Okay, you merge two data points with the closest, with the smallest proximity. Okay. All right. So I guess we stop here. We come back in 15 minutes, 9:02. Okay. Okay, let's come back and continue. So we have talked about the hierarchical clustering with the complete link, which actually using the max distance as the measure to updating the proximity matrix. Okay, so next we talk about the strength of using the complete link, the max distance. Okay, so the strength of using the complete link will make the hierarchical clustering less susceptible to noise and outliers. So which means it is able to, original points, they have different sizes, they're able to be split to two. Yet its limitations also include it tends to break large clusters. Okay, for example, you have two clusters with different sizes, and it is quite likely you're going to produce two clusters with one breaking another. And it will be biased towards the globular clusters. Okay, that means you're likely to be biased towards these globular clusters. So the group average is a mix of the two. So it does not consider the minimal distance as the measure to update the proximity matrix. Also not consider the max. It consider the average. Okay, so that means you actually select all the proximity of all the data points in two clusters. Okay, you consider all combinations, then take all of them and divide by the total number, total combinations. Total combinations, number of clusters in a number of data points in one cluster and another number of data points in another cluster. Okay, so you do a summation, then you divide them to get the average. So the proximity of two clusters is the average of pairwise proximity between points in the two clusters. So hierarchical clustering with group average need to use average connectivity for scalability, since total proximity favors large clusters. Okay. So by using the group average, the nested clusters will look like this, and the dendrogram will look like this. So group average is a compromise between single and complete link. It's taking a trade-off between these two. So its strength is less susceptible to noise and outliers like complete link. Okay. But its limitations is also similar to complete link. It's biased towards the globular clusters. Okay. So that's the group average. So we finished the hierarchical clustering. Any comments and questions about the hierarchical clustering from our audience? So the technical challenging will be the usage of the different measures to updating the proximity matrix. And students will be easily confused by using the measure to updating and the proximity matrix and how to merge and split. They are different logic, okay? I saw in the past in the test, in the exam, like students are confused by these two. So updating proximity will be based on like using the single link, complete link, or group average. But merge of the data points to form clusters, we always look the closeness of the data points, which means they have the smallest distance, okay? Oh, That one basically indicate the number of data points in one cluster. Okay. This one means the number of data points in cluster I, and another means the number of data points in cluster J. Okay. So their multiplication means the total number of combinations of the pairs of data points. Explain the max methods. Okay. Let me explain the max methods. Okay. So the max methods, we need to separate two issues. One is merge data points as clusters. We look their closest distance. For example, when we treat individual data points as clusters and we start to merge, we still pick 3 and 6. We always pick 3 and 6. Pick 3 and 6. Why? Because they have the smallest distance at the beginning stage. Okay, so we will always merge 3 and 6 first. So you will know that the merge okay, so I saw there are quite a number of problems. So first, let me explain the issues that our classmates asked the principal. Okay, then I will answer other questions one by one. So we will see that when we merge the data points, we always consider the minimal distance between two clusters. Okay, so when we have individual points as clusters, then this closest distance between two clusters are equal to the closest distance between two data points. So that's P3 and P6. Yes, 0.11, which is the lowest value in this table, in this matrix. Okay. The things become different when we compute, when we update the distance matrix. So what is different? Once we merge 3 and 6 as cluster, we denote it as cluster 1. So your proximity matrix becomes P1, P2, P4, P5, and C1. Okay, and here the same P1, P2, P4, and P5, and C1. So the distance between P1 to P1, P1 to P2, P1 to P4, P1 to P5, we can copy from the previous table. Okay, they are the same. The problem comes from how can we calculate the distance between P1 to C1, which is the point 1 to cluster 1, the point 2 to cluster 1, and the distance between point 4 to cluster 1 and point 5 to cluster 1. Okay, those proximity or those distance needs to be updated. So proximity basically means distance. Okay. So I use P1 to C1 as an example. So the distance, let me use D as a function, denote the distance between point 1 and C1. Okay. So the complete link will be equal to the maximal between the distance between P1 to P3 and distance between P1 to P6. Okay. Now, compute the central E of P3 And P6 means you are applying hierarchical clustering with the distance of centroid. You can see my previous slides. To updating the proximity, there will be 4 approaches. By minimal, by mean, by max, by group average, and by distance between centroids. Okay, so you are talking about the situation of the last scenario, which is the simplest one. That means you compute the centroids of each of the cluster, then compute the distance. Okay, but there could be other scenarios that you need to use mean, max, and group average. Okay. So Haoling, do you get my point? Yeah. Okay, that's good. So you know what is the max, right? Okay, good. And the group average, the same logic. So Wong Ting Long, Jason, your question is the first stage is considering closest points first in max. I would like to mention again, no matter which proximity updating strategy, mean, max, group average, or distance between centroids you consider, when you merge the data points as clusters, you always consider the closest distance. Okay, you always consider the closest distance. So you can see like later, no matter we let me clear my drawing. No matter we do the single linkage, we first merge 3 and 6, or we do max, we always first merge 3 and 6, or we do group average, we are still first merge 3 and 6. It is because when we merge the data points, we always consider a pair of data points have the closest distance. And you might be further asking, then why mean, why max, why group average? This becomes a case that in a later, after we group 3 and 6, they becomes a cluster. But others are still individual points. Then how can we compute the distance between an individual points and the cluster of many points? Okay. So there are 4 strategies. One is called mean, another is called max, and the third one is called group average, and last one is called distance between centroids. You get my point, Jason? Okay, that's great. Yeah, it's easy to be confused, like typically in the test. If I don't explain clearly, many of students will make mistake. And I remember previous one of our students mentioned, which kind of data need clustering? Could you please give us an example? So which kind of data need clustering? This is a big question. My answer is all kinds of data, if you don't have a targets, they can be analyzed by the clustering strategy. What does no targets mean? That means you don't have a parameter that you want to predict or you want to classify. Okay, so that means the targets. And if you don't have a targets, then how can you analyze the data sets? Then the intuitive way is analyze the similarity among data. So that's why the clustering works, because clustering, no matter what kind of principles, the one fundamental mechanism is they will examine some of the similarity properties among data points, right? So for example, in marketing, you do customer segmentation. This is the data needs to be analyzed by clustering. You might collect data of different customers, okay, their age, their income, their preferences. Then you need to do clustering to make them as different groups. Then you will find out the interesting groups that may favor your products. Then you do promotion, right? So Deng Gege, right? Do you get my point? Or did I answer well your question? Yeah, great. Thank you. Yeah, thank you all for the very nice questions. I think not just you, your questions also help our classmates understand better about the concept. Okay, so we finished the K-means, we finished the hierarchical clustering. Then we introduced the next very famous strategy called DB scan, density-based scan. Okay, so it's a density-based clustering. So we do clustering by scanning the density of the data points in the data set. So DB scan is a density-based algorithm. First, we need to define what is a density. So in this algorithm, so the density here and the density in the statistical learning or statistical distribution is different. So the density definition here means the number of points within a specified radius, which denoted by a symbol called epsilon. Okay. So density here, specifically in this algorithm, it means the number of points within a specified radius. What does that mean? We draw a graph. Given a data points, okay, given a data points. So given a data points, we make it as a star shape and its neighbor as a dot. So we set the epsilon, it's a radius as this long, and it scan a circle. Scan means you swap, okay? Swap the area, then you get a circle. Then you see how many data points are included within this circle. It quantifies density, okay? The number of density means number of data points you included. The density means the number of data points you included within this circle, okay? So first, we finish the definition of density. And the second, we would like to introduce a new definition, a new term called core point. So what does core point mean? So a point will be called a core point if it has at least a specified number of points within the radius epsilon. And this specified number of points means the main points or the minimum points. So it is the parameter specified by you when you use the algorithm. You specify the number of points need to be counted, okay, within this radius epsilon. So these are points that are at the interior of a cluster or counts the point itself. Okay. So for example, you set the main points to 3. Then you set a value of the epsilon equal to 5. Then given data points, you swap, you get a circle. If you, within this circle, you have 3 points, then the default given data points is called a core point. Could I have example later? Yeah, here. So here we set the minimum points to 7 and given an epsilon. And we use ABC 3 points as an illustrative example. So we set A, we're using A as a center, then we swap, okay? Swap the area. So we get a circle. And how many points are included? 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7. So 7 points included. So A is a core point, okay? Because this space includes 7 points, right? So when you count the minimum points, you need to count the points that are at the interior of a cluster. What does that mean? The interior of a cluster means you swap a circle, all the points within this circle. Okay? That means the interior of a cluster. As well as you need to count the point itself. So when you're given a point, it should be counted. Then next, we would like to introduce another term called border point. What does a border point mean? So a border point is not a core point, but it's in the neighborhood of a core point. Then let's look at the example. What is the border point? Okay. So if in this circle, we find out one data points, which we draw another circle, and in that circle, it does not contain 7 data points, which do not meet the minimum points criteria. So the point B is not a core point, but it is the neighbor of another core point A. A neighbor means it is within another swap circle, okay? So B is within the circle swapped by A, so it becomes a border point, okay? It becomes border point. So border point means any data points who are not core points, but who are neighbors of the core points. Okay, so we call border point. Then the third term we would like to introduce is the noise point, or sometimes we call outlier. So a noise point is any point that is not a core point or a border point. So here, the example is C. So C is not a core point as well as not a border point, so it is a noise point. So what does DB-scan algorithm do? So the DB-scan algorithm, first, we're given so many data points. For every data points, we need to do a swap, okay? Then we annotate whether this point belongs to a border point or a core point or a noise point. So if there are noise points, we need to eliminate those noise points, okay? We need to eliminate those noise points. They are outliers. So after eliminate those noise points, then we perform clustering on the remaining data points, okay? Then we set iteration or current cluster label to 1. Then for all the points, all the core points, we do the following things. So start with 1 core point. So if it does not have a cluster label, then we set this core point with a cluster label 1, okay? So label the current core point with the cluster label current with a cluster label, okay? Then end if. Then all points in the epsilon neighborhood, except the ith point itself, we do the following. So if the point does not have a cluster label, then we label the point with a cluster label, current cluster label, okay? Then you will see if we have original points, then after we're using the DB scan, we are able to extract the main pattern, okay? And the points types, we have core denoted by this color, and border and noises, okay? Border and noises, all right? And then we talk about the DB scan. When does it work well? So DB-scan particularly works well when the clusters are mattered with different shapes and sizes. Okay. So for example, this type of data, this distribution is like this, but originally, based on our visual inspection, we will see that already it has some shapes. But use DB-scan, we are able to see it like this. Okay. So the DB-scan can resist noise. It has resistance to noise and can handle clusters of different shapes and sizes. But what are the scenarios that DB-scan does not work well? So given original data points like this, so it has some globular shapes, okay? And especially it has varying densities. You can see some of the data points, they have very dense, and some of the data points, they are very scattered. So in this case, the DB-scan might not work well, okay? It will focus on some particular densities and make some more scattered data points as other cluster. Okay, and also high dimensional data. So it has your data points have a higher dimension, then the density becomes difficult to count. Okay, so you are losing its function. So when you use the DB-scan, you need to determine the epsilon and the minimum points. So the idea is that for points in a cluster, their kth nearest neighbors are at roughly the same distance. That means given a kind of swap, we want their neighbors to have similar distance to the center. Okay, so we can, based on such kind of examination, go too far. Give such kind of idea, we can set the k, or we can set the epsilon length. So noise points have the kth nearest neighbor at farther distance. So we plot the sorted distance of every point to its kth nearest neighbor, and we probably stop in one places. Okay, here. And different aspects of cluster validation. So we finished 3 clusters: DB-scan and hierarchical clustering and k-means. Any comments about DB-scan? No comments, no question for DB-scan, right? Oh, some of the students asked like the logic of this part. All core points do the following things. So we use the later example as a case for this one. Okay. So this one, when we in inspection visually check, we will see that this group of stuff, they are naturally a set of core points. Okay. And this is another set of core points. So when we first do one set, we set its label to cluster 1. And when we go to the next group of core points, because they're disconnected, so there are 2 groups of core points. So this will be a C2. Okay, so such kind of. And others will be the outliers. Okay. All right, so if no comments and questions about 3 clustering algorithm, then we go to a general topic, which is called different aspects of cluster validation. How can we validate the clustering performance? Okay, or how can we validate our clustering results is good? So that there are following aspects for cluster validation. So first is determining the clustering tendency of a set of data. So clustering tendency of a set of data means you want to distinguish whether non-random structure actually exists in the data. Based on your visualization, okay, you already observed that there are some structure there. So there will be some tendency of clustering. And you would like to expect your clustering results will extract that structures you observe with your eyes, okay? Then you're comparing the results of a cluster analysis to externally known results. This means that you might have ground truths of your data sets, but you don't give it to the analyst. You ask the analyst to do clustering results, to do clustering analysis, and see whether the returned analysis results, the generated clusters, match your prior knowledge give labels, okay? Whether match the labels given by your prior knowledge, okay? That's the second point. And third is evaluating how well the results of a cluster analysis feed the data without reference to external information. So basically, you just apply the cluster analysis and you don't do any of the, don't refer to any of the external information and see how the cluster analysis feed the data. And comparing the results of two different sets of cluster analysis to determine which is better. So you can compare based on the SSE of the produced clusters, also kind of. And the last one is determining the correct number of clusters. And this usually, it can be judged by the ground truth, or it can be determined based on, for example, when we talk about k-means, we say the optimal k leads to the minimal SSE, right? So such kind of correct number of clusters. If we have the correct number of clusters, then our cluster analysis can be validated. So for the point 2, 3, 4, we can further distinguish whether we want to evaluate the entire clustering or just individual clusters. So sometimes when you do a clustering, you have you might not be just interested to all the clusters. You might be interested to a particular group of data points, and they should be kind of individual clusters. You might not care about the clustering results of other data points, but you have a strong attention to some particular clusters. So to validate the cluster, produce a cluster, okay, or to check the validity of the produced clusters, we need to rely on some measures. Besides some qualitative analysis, quantitatively, we need to rely on some of the measures. So there are some numerical measures which can be applied to judge various aspects of cluster validity. Okay. So first one is called external index, which is used to measure the extent to which cluster labels match externally supplied class labels. This is called entropy. Okay. And the second is internal index, which used to measure the goodness of a clustering structure without respect to external information, which is kind of fit. So such internal index, one example is the sum of square error. Okay, this describes the fit. And the third one is called relative index, used to compare two different clustering or clusters. So often external or internal index can be used for this function. You can either use SSE or entropy. So and sometimes these are referred to as criteria instead of indices. Okay. So the correlation in measuring the cluster validity. So there are two matrices, and one is called proximity matrix. We have discussed it before. Another is called ideal similarity matrix, which means one row and one column for each data point, and the entry is 1 if the associated pair of points belong to the same cluster, and an entry is 0 if the associated pair of points belong to different clusters. That means you check the ground truth of the data points and the generated clusters, data points in each of the clusters. Then you can do a comparison. You compare the label of each pair of them. Okay. Then you assign 1 if it matches and 0 if it is not. And also compute the correlation between the two matrices. Okay. Since matrices are symmetric, so only a correlation between m multiply n minus 1 over 2 entries need to be calculated. So that is the computational complexity. And high correlation typically indicates that points that belong to the same cluster are closer to each other, are close to each other. Okay. But it is not a good measure for some density or contiguity-based clusters. Okay. So using some similarity matrix for cluster validation. Okay. This is an example. And internal measures, cohesion and separation. So clusters can also be measured by the cohesion and separation. So cluster cohesion means measure how closely related objects in a cluster. That means how dense the points in a cluster. So typically it is measured by the SSE. Then cluster separation means how the two clusters, they are separated from each other. So measures how distinct or very separate the cluster is formed is from other clusters. Okay. So it's called, it will use the BSS. So what is your definition? Howling asks, can we use variations? Then what is the definition of variation, right? What is your definition of variation? How did you calculate the variation? Basically, you need to have some compute the centroids first. It could be an idea, okay? It could be an idea. But here we want to measure whether the clusters, they are dense, they are condensed with, they are containing points, data points condensed within the cluster. And the clusters between each other, they are separated far away, okay? We want to measure whether there are such kind of things, okay? So that's, we use SSE and the BSS, the equations are here. So BSS is equal to absolute value of Ci, that is the size of the cluster I, which means the number of data points in that cluster, multiply the square of the distance between the average and also the centroids of other clusters, okay? Clusters I. Okay, it's a kind of variation idea, okay? So this SSE already consider the data points to the centroids, the variation between the data points to the centroid. And these centroids, how separate the centroids, how the centroids separate from each other. Okay, this is mean of the centroids, which is M. All right, so I guess I will stop here today. We finish the topics in the unsupervised learning. So next, there will be a laboratory section. I will let the TA to give the laboratory in the later classes. Okay. So yeah. So we will call it a day. Stop here, and wish you guys enjoy the contents. And I will see you guys next week. Bye bye. Have a good night. Bye bye.